Okay, so what we are going to practice today is about vectors. So first, both of you write in the chat what you know, what's the difference between vectors and scalars.
Hello.
Hi, can you hear me? Hi, can you hear me?
Sir, are you talking? Because I cannot hear you.
Hi, can you hear me now? Can you hear me now?
Mm. Yeah. Yes.
Okay, that's great. Is it still audible?
Yes.
Yes.
Okay, that's good. That's great. I think something was wrong with my mic, but now it's fine. Okay, so we have started actually the topic physical quantities, which is we are just going to discuss two different types of physical quantities. And actually, our target is to discuss only one, but there are two different types of physical quantities. In physics, all what we study from the very first lesson, that is the distance or displacement or motion or speed, like that, we are studying quantities: distance, displacement, speed, velocity, acceleration, time. Next, what we are going to discuss is momentum, force. The next, what we are going to discuss, work, energy, power. Next, what we are going to discuss is like temperature, current. So from the very beginning of the physics till the last, we are just going to discuss physical quantities. Okay, so these physical quantities are mainly divided into two groups. That's vectors and scalars. So do you have an idea what are vectors and what are scalars? Write in the chat. That's right, Fatma. And what about Tanya? What you know about vectors and scalars? That's right. Vectors do have magnitude and direction both, whereas the scalars are those physical quantity which has only magnitude. So magnitude plus direction. Then those are vectors. And if we have only the magnitudes, then it's the scalar. Scalar quantities can be added or subtracted by simple mathematical rules, but vector quantities are not. But before we go to that, we need some special thing which we say that representation, graphical representation of vectors. So do you know what we use to represent like graphically a vector? So any idea?
We can use like arrows to show vectors.
That's very good. We can use arrows to represent vectors. So arrow has two parts: the length of the arrow and the head of the arrow. So the length of the arrow represents the magnitude, whereas the head of the arrow represents the direction. So the length of the arrow represents the magnitude and the head represents the direction. So that's what we need. So both of you have a good idea about that. So that the length, length of the body is the magnitude and the head indicates the direction. So length, just a minute. So length is direction and the head, oh, what? I wrote it reverse. Length is magnitude and the head is the direction. And the head represents the direction. So that's okay. But how to add vectors? Vectors cannot be added like ordinary numbers. In some cases, they are, like I draw it here, that we have a box here and we are going to push that box. So this is a box and we want to show that we are pushing with a 3 Newton force and a 4 Newton force. So we actually need a scale to show that. So we use a scale to draw. So we are going to push this thing, this black box, with a vector 3 Newton to the right and 4 Newton to the right. So we, first of all, in graphical representation, what we need, what we are going to need in graphical representation, the first thing which we need is a scale. So we are going to draw the force which is made in Newton. So we will use a scale where we make a comparison. Say that I not 4 Newton and 3 Newton. I need 40 Newton and 30 Newton. So these are large values. How I can present them on the page? So for that representation, I need a scale. So where in that scale, I will use the length, like 1 centimeter equals to 10 Newton. So that's what we have. 1 centimeter is equal to 10 Newton. So to show a 30 Newton force, I need a 3 centimeter line. And to show a 40 Newton force, I need a 4 centimeter line. So this blue, you can see that it's 4 centimeter long. So how much is this force? This is 40 Newton. So this is 40 Newton. And I use a green force that acts on the same object, but I draw it 3 centimeter long. If I have drawn it 3 centimeter long, what do you think? What's its magnitude? If it's 3 centimeter long, what's the magnitude of the green force?
30 Newton.
That's very good. It is 30 Newton. So we are pushing the box with a 40 Newton force and with a 30 Newton force. So what's the resultant in that case?
70 Newton.
Okay. And in what direction?
To the right.
To the right. Tanya, is that clear?
Yes.
So we will draw a 7 centimeter long line to show the resultant. So this is the resultant. So the resultant force is this 7 centimeter long line, which actually means 70 Newton. To the right. That's perfect. But we have the same object and we are going to apply the same forces, but in opposite directions. We push it with a 30 Newton to the right, and with 40 Newton, we push it to the left. Then what's the resultant? So what's the resultant now? That's right, Fatma. Tanya, what's the resultant now? That's very good. So we show it with a just 1 centimeter long line to the left. So that's what we have, the resultant. So resultant is 10 Newton to the left. So still nothing special. But what will happen if we have the same object and we push it or we pull it with 30 Newton to the right and with 40 Newton upward? We pull this thing 30 Newton to the right. This time, instead of pushing, I say that we pull it 30 Newton to the right, and with a force of 40 Newton, upward. So what will be the resultant now? You can see that still, if I use the scale, still it's the blue line is 4 centimeter long. I will just show it. No, it's not 10 Newton up. So look, it's still, the blue is 4 centimeter long. So what's the resultant now? Okay, that's very good, Fatma. Your answer is right. My mistake. I just Tanya, it's not 10 Newton. And Zainab, sorry, Fatma, do you know
It's
how?
not up, it's like
Yeah,
it goes across.
across is right, but 10 Newton is wrong. So,
Okay.
Fatma, you have given me the answer of 50 Newton, but do you know how we get that 50 Newton?
You can use the hypotenuse rule.
But that's right, very good. But before using the hypotenuse, do you know why actually we use the hypotenuse?
No, I'm not sure.
Okay, so I just tell you one thing. Even the previous cases, we use a simple rule. How we get that 70? That 70 was actually the sum of the two. We join the two vectors together. We first put a blue vector and then we put the green vector. So you can see that the total length of the blue and the green is how much? Isn't it 7?
Yes.
So that's why the combination of by combining these two forces, and how we combine it, we call this method as head to tail rule. Why this method is called head to tail rule? Because what we are doing, we are connecting the head of the one with the tail of the other, right? So how we are connecting these two things? By head to tail rule. Is it clear? That gives us 70. Is that right? And the same
Yes.
is the reason to get that 10. From that point, just on. From that point, we acted a force forward and we end up somewhere here, right? And from the head of this green force, we draw that same 40 Newton without changing its length or without changing its direction. We draw it by joining the head of the green with the tail of the blue. Got it?
Yes.
So that's where we get our answer, the little red thing to the left. Got it? So this point was the starting point and this point was the ending point. So we draw an arrow joining the starting point of the vectors and the ending point of the vectors when we connect them by using head to tail rule, right? So we use the exact same method here. We combine the two vectors without changing their length or without changing their direction. We combine the two vectors like this. So what is this step called? Head to tail rule. What we are doing, we are combining the two vectors by using head to tail rule. And how we can get the resultant? We can simply get the resultant by joining the tail of the first vector, which in this case is the green one, with the head of the last vector. Got it? So that's what we do. We join the tail of the first vector with the head of the last vector. So that is our resultant. So for this particular question, we can use Pythagoras. Why? Because our vectors make a right angle triangle. Right? Our vectors makes a right angle triangle. Is right? So that's why Fatma said we use hypotenuse. Right? The reason behind that hypotenuse is we have connected the other two vectors which we have to add by a rule called head to tail rule. Got it? So whenever you have to, even in the previous two answers, you have given 70 Newton and 10 Newton because we have connected those two vectors by head to tail rule. So one method is that you can just use Pythagoras. The other, you can still measure the length of this thing by the help of the ruler. So check out, if I place the 0 exactly at the starting point, how long is the red vector? On the scale, how many centimeter is the red vector?
5 centimeters.
Okay, so what we have called 1 centimeter is 10 Newton, right? So 5 centimeter will be 50 Newton. Got it? So that's why that 5 centimeter we write as 50. Is that right?
Yes.
Okay, now that's if they are vertical and horizontal, we can use that. But if we have an object on which we have to exert two forces which are neither vertical nor horizontal, like we have an object and we are going to exert the two forces on it, that's A and B. So say that the force A is 100 Newton. A is 100 Newton at an angle of 25 degrees. 100 Newton, 25 degrees. And the B is 40 Newton at an angle of 75 degrees. So what will be the resultant this time? Can you have any clue? They are not right angle. They are not in the same direction. They are not in the opposite direction. So as they are not in the same direction, we cannot add them. As they are not in the opposite direction, we cannot use subtraction. And as they are not right angle to each other, we cannot use the Pythagoras. So only way we left with is using a scale diagram. So what we will use, we use a scale again. Before we draw it, we will use a scale. So what scale we will write? We have to draw a 100 Newton, so I will draw 10 centimeter. So scale is 1 centimeter is again equal to 10 Newton. So when I have to draw a vector which is 100 Newton, 25 degree, be careful, you will come across this thing when nothing is mentioned, like in this A and B, I have not mentioned anything. When nothing is mentioned with the angle, when nothing is mentioned with the angle, it means anti-clockwise with positive x-axis. Nothing mentioned. That it's with the vertical or with the horizontal or clockwise or anti-clockwise, nothing mentioned. Then what we use? Then we use that anti-clockwise with positive x-axis. That's what we use. Remember, it is always like that. If someone just say the angle, nothing is mentioned. So what we use? We always use anti-clockwise with positive x-axis. So here I have, when I was writing this thing, I have not mentioned that it's with the vertical or with the horizontal, or it's with the positive axis, or it's with the negative axis, or it's a clockwise or anti-clockwise. So it's obvious. That's a rule that we do that. Okay, so that's what we're gonna do here. So we have 1 centimeter equal to 10 Newton. So we need the scale, right? We need the ruler to draw a scale diagram. So we use that ruler here. To draw a 10 centimeter long at an angle of 25 degree. So to draw 25, what we need? To draw an angle of 25, what we need?
Protractor?
Yes, we need a protector. You will place that protector here and then turn your scale by 25 degrees, right? Is that right? And you place it here and you draw a 10 centimeter long line. Got it? But you know that you have to use the protector, but I have, like, I'm using a software, so I have a freedom. My ruler has a protector. You can see that 25 written it inside it. So my ruler has a protector in it. So I know that right now my ruler is 25. Look at it. The angle get changed as I turn it. Got it? So it's 26 right now. I make it 25. So that's 25. So I have mentioned that green vector, the vector A, is 100 Newton. So 100 Newton will be 10 centimeter long vector. Got it? So that's 100 Newton at 25. And what we have used that 25-degree with a reference horizontal line. The reference line which we have chosen is along the horizontal. Got it? Is that clear? How we draw that 100 Newton at 25?
Yes.
So we will use the same technique. We will use the same horizontal line, and we will at the head of the, because to add the two vector, what we need to do, we need to connect them with head to tail rule. So we use that head to tail rule from here, and like we apply it at this point. Just wait on. Okay. So to join the second vector, I draw the second vector at the head of the first one. So I again use like the scale. So when I use the scale, I need 75-degree angle with the horizontal, and I need to draw a 4 centimeter long line. Right? So I put my scale here. I turn it by 75 degrees. Got it? I make it sure that the 0 is at the head of the first vector. And I draw a blue vector, the B vector, which is 4 centimeter long, to show 14 Newton long vector. Got it? So this is 40 Newton at an angle of 75 degree. And how we have drawn these two vectors? We have already drawn these two vectors by head to tail rule. Is that right? So we do
Yes.
have our both vectors, 100 Newton at 25 degree. This vector is 100 Newton at 25 degrees. And the other vector is 40 Newton at 75 degrees. So that's 40 Newton, which I'm going to write here, 40 Newton. And actually it is at 75 degrees. So how we can get the resultant? Just measure the length from start till end. By using the head to tail rule, we can measure this length from the start till end. So first we draw the resultant by joining the tail of the first vector with the head of the last. So that's the resultant. I call it the resultant vector C. So what's the magnitude? We do have the magnitude of the A, 400 Newton at an angle of 25. We do have a vector B, which is of a magnitude of 40 Newton at an angle of 75. So that C, which is actually the resultant of A plus B, what's the magnitude of that? So what we will use? We will use a ruler, because that's what we are using to draw the figure. Okay, so we will put our ruler here and check how long is this vector. Got it? So we put the 0 at the start and we turn it to align it with the given vector. So when we align it, we get this. So it's almost 13.8 or like that. Got it? You can see that it's what it is, 13.8. Is that right? Oh, not 13.8. Why I write 13.8? 12.8. Is that right? The length is 12.8 centimeter. So 12.8 multiplied by 10 is 128 Newton. Got it? So that's the answer. Is it clear? So this method is called scale diagram. Right? How we added the vector? By the help of a scaled diagram. Is it clear how to draw these scale diagrams?
Yes.
Okay, that's great. So, but this thing is always a problematic. It's a time consuming. If your pencil is not sharp and if you're not good at adjusting your scale or ruler, you will end up with the wrong answer. And the direction is 39. The angle is 39. So I do write the answer here. So the answer of this thing is 128 at an angle of 39 degrees. Got it? So that was the resultant of the two forces. Is it clear, this part?
Yes.
Okay. Now we use the same figure, but okay, I will use the same figure later. But first, there is a thing which is called, any question about vector addition by a scale diagram and adjusting this diagram figure like thing, how to get the resultant?
No, no question.
And Tanya, you? Is there any question from your side? Tanya?
No,
Okay, that's great.
no question.
Okay, so what we have next is, we call this thing as rectangular component. So do you have an idea about the rectangular components of a vector?
No.
Okay. In the previous example, what you can say, isn't A and B are the two components of C? If you add them together, if you join those components A and B, you will get the C. Is that so?
Yes.
So A and B are the component of the C. Similarly, we can draw many other components for any given vector. So if we have a given vector, we can draw a lot of component for that vector. Okay, we can draw many components. Like these two gray, if you add them, you get the black resultant, right? If you add these two gray, you will still get the black resultant. So these are components. These things are components, right? Even these two are component. Got it? Even this, just a minute. And this is component. So if there's any two vector which you add together and they give you a resultant as the vector, those two parts are called component. But such two components which makes an angle of 90 degree with each other. Such component which makes an angle of 90 degree with each other. So these two red components are not they like an angle of a rectangle, one side of a rectangle, these two red ones, because rectangle has all the angle made up like 90. Is that so?
Yes.
So that's why these two components are called rectangular components. Is it clear?
Yes.
But remember, not only these two are the rectangular component. We can prove it by showing it with the help of a protector here. Oh, sorry, set square. So we use a set square. So you can see that the two vectors which we have drawn, they are at right angle to each other. Is right? You have any two component which are like I just adjusted. So look at this thing, which I'm going to draw right now. These red things are again at right angle to this resultant. So these two red are also making an angle of 90 degree. Are they making an angle of 90 degree? Can you see that? The two other red, because I have used a set square. Set square is used to draw an angle of 90 degree. Can you see it?
Yes.
So not just these two, you can have many other also drawn as a set of rectangular component. Like you can have a rectangular component, just wait on. These two are also rectangular component. Got it? So all the reds are rectangular components. Even just don't. This one. So as long as the two components are at right angle to each other, we can draw them as rectangular components. We can call them as rectangular component. Is it clear?
Yes.
So every vector, every time it can be divided into two rectangular components. By vector, we mean a vector whose magnitude and direction is known. Say that we have a vector here and we call its magnitude as A and we call its direction as theta. So if I call this vector as A, so there are two components, one along the x direction, one along the y direction, but I will not use their name as x and along x and along y. They have a proper name, and don't try to use the base and the perpendicular. Try to use the word opposite and adjacent. Are, are you familiar with these words? Are you familiar with these words?
Yes.
So these are the side which is adjacent to theta. That side has a name adjacent. The side which is in front, like you said your address opposite to that building, so it means it's front. So the side which is opposite, that side is called opposite. The one which is opposite to theta, got it? That side is opposite. So not to use perpendicular, vertical, or horizontal like that, or base like that. Use these words adjacent and opposite. So the other thing is the 90-degree angle. In this case, the 90-degree angle is with the red lines, rectangular components. So when we use those rectangular components and to claim that angle is 90, so remember the side opposite to 90, not opposite to theta, the side opposite to 90, that side is the hypotenuse. Is that right? So in terms of A and theta, can you let me know what will be the adjacent magnitude of the adjacent side? In terms of A and theta, how much is the magnitude of the adjacent side? Can you say that? What will be the magnitude of the adjacent side and what will be the magnitude of the opposite side? Like not the value, but the formulas in terms of A and theta. Any idea? Okay, no problem. I make it easy. I say that
The adjacent might
yes.
be. Won't the adjacent be like hypotenuse minus opposite?
Okay, just wait a moment. I just give you the values. I know that you know that, but you actually, in the background of your mind, you have no idea what you are doing, but you can easily work it out. Say that this has a magnitude of 100. This right, black side has a magnitude of 100. This angle is, say that 30-degree. Find the length of the adjacent side. Find the length of the opposite side. You can use trigonometric ratios. You can use the trigonometric ratios, the sine, cos, and the tan thing like that. prior to workout and write in the chat. Are you both working?
Yes, just give
Okay.
me a minute.
Okay, that's great. And that's right, Fatma. Tanya, do you have an idea what to do? Are you working?
Yes, I'm just solving it.
Okay, that's good. Fatma, till then, can you write what formula you have used actually for the opposite and what formula you have used for the adjacent?
Okay.
So Tanya, are you familiar with this thing which what I have written?
Yes.
So we have to actually use this. Oh, it's actually A. Hmm. Tani, that's answer is not right. Maybe your calculator is not in degrees. It may be in radians. Make sure your calculator is in degrees. So from this formula, the one we have written on the top, from this one we have sine theta equal to opposite our hypotenuse. So from here we get what is wrong with this? Just around. The top one is the sine theta is equal to opposite our hypotenuse, and this will leads to opposite is equal to hypotenuse times the sine theta. Is that right? Exact same way, the bottom formula is for the cos theta. So cos theta is equal to adjacent over hypotenuse. So if we rearrange it for the adjacent, adjacent is equal to hypotenuse times cos theta. Is that right? So when we use the values, we get 100 sine 30. So opposite actually equal to 100 sine 30. And the adjacent is 100 cos 30. Is right? And that is actually equals to 50, and that is actually equal to 86.6. Is that fine? Tanya, is that clear?
Yes.
So that's what we get. And when we have don't when we don't have the values and we have just the names a and theta, then how we write? A can be replaced with any other force or like any other vector, d or like s or h or anything. So if we have a as the hypotenuse and theta is just theta, then the adjacent, what we have written on the top, then according to that, the adjacent thing is, then we have the adjacent thing equal to a cos theta. Just a cos theta, and the opposite thing is a sine theta. Remember, although I'm going to name it later, but till now I have not named it ax and ay. You know that we do have these variables ax and ay, the component of the a along the x-axis and the component of the a along y-axis. Do you use these terms? The component of a in the x direction is ax, and the component of the a in the y direction is ay. Do you use these terms, ax and ay, or any?
Not here.
Okay, no problem. So the component in this figure, it's ax, which is a cos theta. And in the above figure, like the opposite side, it's the ay, the component of the a along the y direction, that's ay, and that's equal to sine theta. Why earlier I have not used it? No doubt 70 to 80% your cases ax will be a cos theta and ay will be a sine theta. But this thing is not the rule. This thing is not the rule. The rule is opposite and adjacent. Opposite will be the cos component, opposite to theta will be the sine component, and adjacent to theta will be the cos component. That's the rule. So why it's not like I said, we are going to discuss. So look, I draw it here. So it's the same figure. So x is the cos theta and y is the sine theta. But if I use the same figure and I turn it, just a second, I turn it this way. So what you think now? Which x and y are not they get switched?
Yeah.
So what we will do now? So here, actually, when we write the things, we will write them accordingly. We will say that this is the ax, and that's actually the opposite. So that's the sine theta. Got it? So ax is a sine theta. Got it? And ay is a cos theta, isn't it? So you can see that the sine and the cos value get switched. Ax and ay value get switched. Is that right? Isn't it? In one case, ay was cos, and in the other case, ay was a sine. Got my point?
Yeah.
So that's why don't rely on x as the cos and y as the sine, because they can switch. What will not get switched? In the above figure, in the sideways figure, or like this one, in both cases, opposite is the sine component and adjacent is the cos component. So this thing will never get like switched. Opposite to theta is always the sine component, a sine theta, and adjacent to theta is always a cos theta. This will not get switched. No matter what way you make the triangle, this will not get switched. It's always like that. Opposite will be the a hypotenuse times the sine theta, and adjacent will be hypotenuse times the cos theta. Is right? So use adjacent and opposite in language rather than using x and y, because if you use x and y, they may get switched when the figure change the direction. Got it?
Yes.
So this is a thing which we need. What's the benefit of this? The benefit of this thing is that we can add vectors by using this thing without drawing a vector diagram. So I picked the vector diagram which we have earlier, which we actually have solved, and we have the answer. So that vector diagram was, just a second. So the vector diagram which we have added is this. I just cloned that page and I just put it at the end. So we have already solved this part. We have solved already this triangle by a vector addition rule. Is right? By a scale diagram method. So our answer of the resultant is 128 Newton at 39 degree. Is that right? We have already worked it out, but we worked it out by using a right angle triangle. Oh, sorry, by using a scale diagram. Now what we are going to do, we are going to work this thing out by using a rectangular component thing. So if A, like the green vector, has a magnitude of 100 and angle of 25, so its adjacent component will be A cos theta and the opposite component will be A sin theta. So can you find out the magnitude by using that adjacent is always the cos component and opposite is always the sine component. So that will be 100 cos 25 and that will be 100 sine 25. So can you find the magnitude of the both? Although right now I'm going to name them as x and y because they are in the direction of x and y, but x is adjacent, that's why it's A cos theta. So using the value of the A, which is 100, and the value of the theta, which is 25, can you work out the value of the ax? And similarly, using the value of the A and theta in A sine theta, can you work out the value of the opposite? So can you tell me the values of ax and ay? Both of you hurriedly write the answer. A is 100, theta is 25. So what are the answer of the ax and ay? Work out the values of ax and ay, write the answer in the chat. Fatma, you should, earlier you did it quite like quickly. Why you are taking some time right now? You can easily write the answer. Any problem? That seems to be the right
No.
answers. Fatma, check your x and y. Have not you switched the values?
Yes, I switched them. Sorry.
Tanya, are you working the values?
Yes.
Okay, and Fatma, you work out exactly the same way as you have worked out the values of ax and ay. exactly use the same technique to find the value of the bx and by by using the value of the b and the theta for the b. Okay.
Okay.
Can you do that?
Yes, I'll try.
Good, Tanya. That's the right answer. Similarly, work out the value of the ay, then bx and by. That's right, Tanya. Very good. Similarly, work out the value of ax and ay. Okay, that's good. These are the right answers. Very good, Fatma and Tanya. You have also, both of you have worked out the right answers, so that's good. So 10.4 and 38.6. So just a second. 10.4 and 38.6. So once you work out these values, you can add the horizontal, the x component separately, and the y component separately. So look, if we want to find the red vector, because our target is to find the red vector without using a scale. So red vector has two components also, just like the we have drawn the two component for the green, and we have drawn the two component for the blue. We can draw the two component for the red. I draw them with a light color. Just a second. So this is the horizontal component for the red. I will just make it a slightly change in a moment. And we have the horizontal component as well. Just give me a second. I will make them slightly like dim and a bit bold so we can see that. So these two components are for the red one. Now we don't have the value of the red, C, but we can still find by the calculation which we have earlier made the magnitude of these two red. I make them pink in a moment so that they appear as the components, and I make them a little bold and a little transparent. So can you find the length of both pink horizontal and vertical component? That's the adjacent and the opposite component. So look, if you add that little bx into, just don't, if you add that little bx into ax, don't we get the whole pink vector in the x direction?
Yeah.
So what you think, what is the length of that pink vector? What is the length of that pink one? I make it a bit red and a bit bold, more bold, like that. So what's the total length of that red one, horizontal red? The green part is 90.6. The blue part is 10.4. So what's the total length of the red thing? Really? Okay. 90.6 is the green part from AX, the length of the AX, and 10.4 is just the length of the blue part. So what is the total length? Look, I'm asking this bottom red one. 101 is right. Tanya, what's the length? Adding 90.6 and 10.4, what you get?
101.
So
101.
that's right. So that's the length for the red horizontal component. Use exactly the same technique to find the magnitude of the vertical red component. You add this 42.3 into the above 38.6. Got it? So 42.3 and 38.6. So what will be the length of that red component which I'm going to highlight? So what's the length of this red one now? That's the right answer. So you have the adjacent and opposite component for the red. The adjacent component, which is the horizontal one, is 101 and other is 80.9. So if you have these two components, how you can find the red hypotenuse? Use Pythagoras theorem and check what you get the value for the red hypotenuse. This red line. Are you working the values? Okay, Fatma get disconnected. Tanya, can you, okay. Tanya, can you hear me?
Yes.
Okay. So are you working the hypotenuse by using the
Yes.
opposite square? Okay, so work it out. Fatma, have you worked out the answer yet or not?
I got disconnected. Can you repeat the question?
I said that you have 101 as the adjacent side length for the red triangle and 80.9 as the opposite side length for the red triangle. Can you find the length for the hypotenuse? That's right, Tanya. What about you, Fatma? Work it out. Oh, Tanya, check it out again. And not the sum. You have to use the Pythagoras theorem, isn't it? Remember, you used 3 plus 4 as the 5 in the first case.
That is what I did.
Sorry, Fatma. Tanya, your answer is right, Fatma.
Okay.
That's right. So that's how we can get the answer to this question without using a scale diagram. Okay, 129.4. And you can use the same 80.9 and 101 as opposite and adjacent to find the theta. So what will be the theta using these two sides? Can you let me know the theta? That's right. So the angle is 53.2. Check out 53.2. No, that's not right. 80, you have to use tan theta. Theta is equal to opposite, tan inverse of opposite to adjacent. Theta will be, because you have to use opposite and adjacent in tan theta. So you use this formula. Opposite over adjacent is equal to tan theta. So kata. So opposite over adjacent is tan theta, or just I write the other way around. Just a second, please. So we have tan theta equals to opposite over adjacent. So theta will be equal to what? Tan inverse of opposite over adjacent. So when you work it out, what you get? That's right. Tanya, what you get when you work out this thing? We get 38.7 or like that. Is that okay, Tanya?
Yes.
So that's what we get. We can get the answer by using rectangular component, and it's always, no matter what's the question, it's always the same procedural steps. What are the same procedural steps? We have the two vectors A and B, which we want to add. So what we did, I write the things here again, which we actually practice. We have A as 100 Newton at 25 degrees. And we have the B that is 40 Newton at 75 degrees. So what is the first step? Find their rectangular component in X and Y direction. So when we did that, AX is 90.6 by using the trigonometry adjacent component. AX is A cos theta. And we get an answer of, just a second, please. Okay. We use AX is equal to A cos theta, and we get an answer of 90.6. And we use AY as A sine theta in this case, which is 42.3. Once we're done with this, we do the same thing with the B components. So we work out the BX, which was 10.4, and we work out the BY, which was 38.6 by using the same B cos theta and B sine theta. So when we add these two things, we get the CX, the resultant X, and the resultant Y. So CX, which is actually the sum of the AX plus BX. So we get 101, and CY is AY plus BY. So that's what we get as 80.9. So once we have the horizontal and the adjacent, what we can do, we can find their rectangular, we can use the Pythagoras theorem to find the resultant, right? So we use the Pythagoras theorem to find the resultant. So the magnitude of the C was Cx square plus Cy square root. So when we use that, we get an answer of 129.4. Got it? We get an answer of 129.4. And the theta is the tan inverse one. Opposite, which is the y component in this example, Cy, because we want to find the theta for the resultant. So the resultant is the C. So tan inverse of the C opposite component, which was Cy, and the adjacent component Cx, which we get as 38.7. So that's how we can find the magnitude of the resultant force, is right, in that direction. Got it? So these steps are always the same. What are the steps? Find x components, find y components, find x component, add x to get resultant x, add all x component to get resultant x. Got it? And find y component of all vectors, like we did a and b, add all y components and get the resultant y. Is that right? Once you have resultant x and resultant y, what you can do? You can use the Pythagoras theorem to find the magnitude, and you can use the like a tan inverse formula to find the angle. Is that right? Is it clear? So these steps are exactly the same. Find x component, add x to get resultant x. Find y component, add y to get resultant y. Once you have the x and y component, you just use trigonometry, Pythagoras theorem, and you will get your resultant magnitude, and you use the tan inverse formula to get the angle. Got it? Is that right? Any question from this procedure which we have practiced?
No.
Uh, Tanya, you any question?
No.
Okay, that's great. So what we are going to do right now, we are going to practice this thing in some questions, okay? Just give me a moment, I upload some questions. So we'll use this thing here. Practice question number 18. Okay, that's right. Tanya, Fatma, your answer has a little problem. A and B were the possible answer, but look, if we draw the thing, which vector is going more down or which vector is going more up? Vertically, which vector is having a greater component? Which vector has a greater vertical component?
E.
Out of P, no, look, the P has only this much vertical component, isn't it? Look at the component of the Q. Isn't it bigger than P? So upward component is small, downward component is more. So will it be slightly upward or slightly downward? When you,
Slightly downward.
that's right. So that's why the option is A. Got it?
Yes.
Okay, that's a very interesting one. And it's easy, but like just question 21. That's right, Fatma. Waiting for your answer, Tanya. Tanya, are you working on your answer? No. Vector. The tricky part was vector. You are adding these quantities as vector addition. So which of the option is a vector quantity? Only one option.
Velocity.
So that's the right answer. Try this one. Question 24. Fatma, again, same mistake. Why not A and why C? What's the difference in A and C? Which one has a shorter vertical length in the answer and which one has a longer vertical part? If you compare the
C is
answer,
longer vertically.
so out of 4 Newton and 3 Newton, which part is longer? The vertical one or the
3 is
horizontal one?
longer
Oh, 3 is longer as compared to 4.
vertically.
No, as compared to 4. Because one out of the C and A, the difference is C has a longer vertical component and A has a longer horizontal component. Got the point? In this
Yes.
will be
Yes.
3 and this will be 4. And in this, it will be 4 and it will be 3. Got it?
Yeah.
So the answer is A. Tanya, is it clear?
Yes.
Okay, that's great. Quickly find this component, question 25. Okay, I have to check it. So it's 5 and it's the adjacent component to theta. Remember, it's the adjacent component. So 5 cos 53. So let me check it out. It's A3. Tanya, it's 5 cos adjacent component to theta. Isn't that one is adjacent to theta? Oh, sorry, my mistake. They have asked vertical. So it's 4. Vertical is 4. Tanya, your answer is not right. Vertical is 4 because the vertical component is 5 sine 53. You can check it. Adjacent was 5 cos 53. That's why I said, remember always adjacent to theta and opposite to theta. Adjacent to theta is the cos component and opposite to theta is the sine component. Is that right? Is it clear, Tanya?
Yes.
Okay, that's great. So that's it for today. Any questions you have from what we have practiced today?
No
Is there any
questions. But the recordings, are you going to share them? How are you gonna share
Yes,
them?
I'm going to share the recording. It will be like because recording gets really long and they take a lot of space, so they
Mm,
cannot be shared on like easily on even on email or like on the WhatsApp. So the easiest way is that I will put it on the YouTube, some channel. There's no like traffic on that channel. No one is there. Like I have no like a large. I just made that in during the COVID time, but I didn't upload it.
what if you mail it to us?
It will take a longer time. I have seen that mail is a bit problematic. You can easily check the YouTube link, and if you want to download it from there, it will be better from there. Because otherwise, I have to mail everyone, and like that, sometimes the mail get disconnected, and like I don't know whether it's received or not. So on the YouTube, it's just there, always there, isn't it? I will upload
Yeah.
with the lecture date, so you can just like search the date. Okay.
Okay.
So the last lecture, first lecture maybe I have not recorded, but the last lecture is uploaded there. Okay. First
Okay.
lecture was not recorded, but this lecture, even this one is recorded. So I will upload it there. Okay. And these whiteboard files, you will get those along with the like these files, the whiteboard files that I will share in the WhatsApp group. Okay. These files will be shared
Okay.
as
Thank
a
you.
PDF file in the WhatsApp group. So that's it for today. So thank you. Have a nice day. Allah Hafiz.
Allah Hafiz.
Thank you, Allah Hafiz.